Good evening, everyone. You all are warmly welcome for this webinar conducted by Institute of Engineers Sri Lanka along with IESL Puttalam District Center. Renewable energy is a topic that is now being explored extensively around the globe. Even in Sri Lanka, we are concentrating our efforts on increasing the portion of electrical power generated by renewable energy sources. As we identified it is as a timely requirement of our country at the IESL Puttalam District Center, we decided to raise your knowledge and awareness on the subject through a webinar so that we have a well-experienced, well-known professional in this field with immense amount of research and practice. I introduce the resource person. Let me brief how we will be conducting the session today. During the first part of the webinar, we will listen to the presentation from our resource person. While the presentation is going on, you can raise your questions in the chat box and our members will be recording all your questions. Soon after we complete the presentation, we will be moving to the Q&A session. And during that period, we will be presenting your questions to the resource person. And we will make sure to address your questions as much as possible. So let me introduce our resource person for the benefit of the audience. He is none other than Dr. Tilak Siyambalapitiya. I would like to warmly welcome you for this occasion, sir. And let me introduce him first. Dr. Tilak Siyambalapitiya is the Managing Director of Resource Management Associates Private Limited. And he earned his PhD in electric power engineering from University of Cambridge in 1988. And for 10 years, he worked in Ministry of Power and Energy, Sri Lanka, and at electric utilities in Sri Lanka and abroad. So he have immense amount of experience in this field. And presently, he is working as an energy consultant. He is a visiting lecturer at many universities in Sri Lanka. So with that note, I would like to warmly welcome you again, sir, for this occasion. So I would like to hand over the control. The screen is yours, sir. Over to you.
Fine. Thank you very much, Mr. Sabri, for the introduction, and to your Puttalam District Center for the opportunity to share some of my past experience in handling or managing or supporting issues related to renewable energy for electricity generation. So I think I will take about 40 minutes for the presentation. And at the outset, I have to tell you, as I have said very clearly, my presentation is about the historic development and the achievements so far and the emerging challenges. So I will stop at that by explaining the challenges that we need to resolve, not only technical, but financial as well. But I will not be talking about the solution to the frequently discussed 70% target, 80% target, or 100% target, but largely working on the issues that we need to resolve as we go forward. So with that note, let me start off with my slide presentation. I will be as brief as I could to the best possible extent, but frequently I find it to be useful to make our active engineers knowledgeable about what has been achieved, because there is a misconception in the society that Sri Lanka is not doing anything. Sri Lanka has not done anything, and for the accelerated development of renewable energy. So let me give you the facts, and then you can decide whether Sri Lanka has done enough or not enough in the past. I will throw at you some challenges that the system is facing in its march towards a larger integration of renewable energy into the grid. So having said that, what you see on this picture on my cover is the Mana wind power plant. So I've been fortunate to be associated with the wind power plant in Mana. We were requested by the government in 2011 to conduct a resource assessment in the Mana Island. So that was our first engagement with Mana. Before that, we know CEB had conducted some basic resource studies. And since 2011, then we went on to develop a master plan for wind power development in Mana. That means a Mana district, in which we concluded that the capacity exploitable in Mana district alone is 375 megawatt on land wind development, not offshore. Offshore will be extra. And even we went on to do the feasibility study for the first 100 megawatt. And we are, of course, happy that CEB took over the development. That was in 2018. And over 18, 19, and 2020, the power plant was fully developed, and it reached the full capacity of 103 megawatt of electricity production around July this year. So it's performing as expected. So let's see what other power plants are doing and what challenges are there. Sri Lanka does produce a lot of electricity using renewable energy, but let's take a step back and examine how much of renewable energy is there in our total energy mix, which will give you an understanding of how much of different types of energy are we using. Now, mind you, this slide is about the primary energy supply. Primary energy supply, which means all forms of energy into the economy of the country. I picked 2018 because that is the year for which the total energy is already published. So it takes a couple of years for the Sustainable Energy Authority to collect all data and conduct surveys for missing data and publish this information. So petroleum looked after 40% of our energy requirements, accounting for the largest share. Biomass, more than half of it is informally used, was 36%, 10% from coal, and 10% from major hydro, and 4% from non-conventional renewables. You will see electricity is not there in this pie chart. That is because electricity is not a primary form of energy. Electricity is always converted from a primary form to a secondary form. So electricity is a secondary form of energy. So if you want to explore more, Sri Lanka's energy data right from year 1970 is published transparently. You can go to the website energy.gov.lk, Sustainable Energy Authority website. And if you want to learn how much of electricity was produced from such a power plant by such an year, that information is available online for anybody to see and conduct further research on. When you consider the final energy, the amount of energy that a customer uses, electricity accounts for 12% of that final energy. So it's not a large share. So if you look at the shares of final energy, that is only a small amount of coal is directly used in industries, because some of this electricity includes coal converted to electricity, hydropower converted to electricity. Then, of course, 46% of energy comes from biomass directly used in the households and industries. Here again, the petroleum products is a very large share of the total energy picture. So having looked at the broader energy picture, we will now focus on the electricity sector. So what you see here is the 10-year development from 2011 to 2020. the share of electricity produced from fossil fuels and renewable sources on the left-hand side. So as you see, the quantum of renewable energy, mind you, the vertical axis is in the form of energy, varies significantly. 2013 and 2018 are very significantly a high renewable energy years. The diagram on the right-hand side perhaps is easier to read because it's in percent terms. So as you see, 2013 was a good hydrological year, and similarly 2020 was moderately strong renewable energy contribution. So this shows how much of a difference can hydropower do to the total energy mix that goes into electricity production. Moving on, we talk more frequently about new forms of renewable energy. Sri Lanka uses different terminology to refer to the modern forms of renewable energy development for electricity production. But the official term that Sri Lanka uses for solar, wind, biomass, and mini hydro is non-conventional renewable energy. But anything that is non-conventional 20 years ago has now become somewhat conventional. So I would hesitate to say that solar PV is any longer non-conventional, because solar PV has been around very visibly for the last 15 years. And mini hydro has been around visibly for the last 150 years. So I would hesitate to call these non-conventional forms of energy, but these are different. These are not hydro power plants, which are backed by larger reservoirs, which are represented by the green portions of the bar. And you will see, as a percentage, Sri Lanka has been absorbing a growing amount of electricity as a percentage from non-conventional renewable sources of energy. So in terms of targets, as you know, we are frequently talking about targets. So the first target that Sri Lanka ever made was on the target of 10% of grid electricity to be met with non-conventional sources of energy. That target was established in 2008 in the National Energy Policy, and I was happy to be a partner in the writing team of the National Energy Policy of 2008, and we debated heavily what target to put in with calculations. It was not an assumption, with calculations, with the correct policies, and with the correct incentives. Sri Lanka reached a 10% contribution from non-conventional renewable energy by year 2015. In fact, Sri Lanka achieved 11% against the 10% target. So the first milestone and the initial targets are easier. And thereafter, Sri Lanka moved on without a very solid target until year 2020, in which suddenly we get a 70% target being talked of in the policy documents or in various political documents. So we will come to that later. I would not want to make this discussion a debate about targets. We would rather discuss the engineering and the economics that goes into the renewable energy development. Now, there's another important factor that we will have to know as engineers, and when we talk and present renewable energy related information. The diagram that you see here is a little bit complicated, sorry about it. The share of renewable energy in the grid. So we have to be clear, what share are we talking about? So I've traced from 1970 to year 2020, which was last year. The blue line indicates the total quantum of renewable energy used for electricity generation as a share of the total amount of energy. So in other words, in year 1983, only 57% of electricity was produced using renewable energy. It was a very dry year. I still remember my first year after graduating as an engineer. It was a very dry year and there were difficulties, there was load shedding. So the blue line indicates the share of renewable energy based electricity in the grid. Now the orange line indicates the renewable energy based electricity generation capacity. So capacity share was say 70% in this era, but the energy share was 95%. So what it means is that the balance 30% of capacity was thermal, and that thermal share was very sparingly used. It was there, but hardly ever used. So the orange line, as you see, as we come into the 1990s and into year 2000 and onward, the orange line crossed the blue line, and now we have a higher capacity share of renewable energy than the energy share. Now, what does it mean? What it means is that our capacity factor of renewables are reducing. So we have a larger capacity share, but a smaller energy share. Before 1995, it was the other way about. Then in the same diagram, I've shown in green the line that shows the share of energy from non-conventional renewable sources. So we'll come to that in a moment in more detail. So it rose up to 11% in 2015. 2016 was a dry year, and it caught up, and last year the share was 12%. So these are the numbers that you may like to remember, that we have achieved 12% from non-conventional sources. But if we put everything together, including large hydro, we have to read it on the left-hand side axis, that we were 37% renewable last year in terms of energy. Why I emphasize so much on this capacity share and energy share is because some countries report the renewable energy share in terms of capacity. So therefore, renewable energy share in Sri Lanka is already at 50%. So if somebody says we want to go to 70%, we only have a little bit more work to do. But running up from 37% to 70% will be a challenge if we want to do it over the next 10 years. So that's why I'm pressing so hard to understand the capacity and energy separately and clearly. We move on. Now, why did the renewable energy share drop in the 1990s? It was the end of major hydropower development. We know that the Mahaweli hydropower developments were accelerated and concluded by 1990. And the remaining large hydropower plant in 1992 was Siyambalapitiya project. So thereafter Siyambalapitiya, for a long period, Sri Lanka did not have any hydropower plant commissioned. So the other hydropower projects such as Kukule, Apakotmale, both of which are in operation now. Broadlands has been under construction for quite a number of years and it's about to start operations now, have taken a long time for implementation, and they are relatively smaller as well. So, of course, the seniors among you will remember the debates that went on about Kukule. Kukule is capturing water from Kaluganga. Apakotmale is capturing water from the upper reaches of Mahaweli Ganga. So the debates that were there and the protests and approvals, disapprovals. I will just take one example. Apakotmale feasibility study was conducted when I was the Chief Engineer, Generation Planning, CEB, 1992. And the debate went on and on and on. And the construction actually started in 2006, 14 years after the feasibility study was concluded, and for a design that was of a lower capacity than the original plan. So finally, it was commissioned around 2012, and now it is operating very well. So there have been challenges in getting more hydropower into the system. In spite of the fact that the whole world and the whole society is asking for more and more renewable energy. Of course, other forms of renewable energy in the 1990s were still too expensive. I'm talking about 1990s, were still too expensive, or the technology was still being developed. But the country was facing a challenge of electrification, and which the country met with a 100% headline, 100% electrification declared in 2016. But remember, in 1990, only 29% of households had electricity. So it was a challenge that had to be met, and it was met by 2016. Now, I said I will talk more about what has been achieved rather than about the future, leaving the future subjects to someone else. The first milestone towards small-scale renewable energy development was in 1996. What did Sri Lanka do? Sri Lanka declared that the grid will purchase electricity at a predefined feed-in tariff. That means it is a fixed price, but annually recalculated. But it is not a negotiable price. There will be no bidding. That means no tendering. But the price is on the table. If you like the price, and if you have a site, you invest, build a mini hydro, sign a 15-year contract, and your electricity will be purchased. So that's what is commonly known as the Small Power Producer Program, which started in 1996. And again, I'm personally happy to have been very seriously involved, sometimes in fierce debates and discussions about the pros and cons and how to take this forward since 1996. So we come in, what was offered, the program was defined as a small power producer program. It offered a standardized, non-negotiable agreement at a tariff. And it was called, in the international jargon, it's called feed-in tariff. So the feed-in tariff was annually recalculated, and it reflected the amount of money saved as a result of building renewables. So that means if there is oil cost saved, the calculation reflects the cost saving in oil. So that program went on till 2007, and the government looked back and saw, look, although it's open to all forms of renewable energy, only mini hydros are being developed. So what was the problem? So the problem was that the other forms of renewable energy conversion to electricity were not viable at the prices offered on the basis of avoided costs of thermal generation. So in simple terms, let's take an example. If Sri Lanka was producing electricity using oil at a price of 10 rupees, the price offered for mini hydros or for any form of renewable energy will be 10 rupees. But when you do the economic calculations of a businessman who does a financial model for his future power plant, he would say, look, mini hydro is good, viable, but a wind power plant is not viable because the wind equipment was still too expensive. So therefore, Sri Lanka made a policy change again in 2007, and it was effective from 2008. For new renewable energy projects that were signed up, they were offered a cost-reflective tariff. Cost-reflective, not cost-based. So therefore, cost-reflective means the ministry, for example, assumes that a wind power plant will cost $1,800 a kilowatt of investment. And the ministry will also assume that it will produce electricity at an annual capacity factor of 32%. So one might argue, okay, it could be 32% here, 38% there, but then some number has to be brought in. Of course, after a lot of studies, it was decided certain parameters were defined. I will not go into all those details. And new contracts were signed from 2008 on that basis. So therefore, mini hydro has one price, wind has another price, biomass another price, and solar PV another price. So based on this, the development of renewable energy projects other than mini hydro accelerated. So today, we have a total of 270 so-called small power producers with a total capacity of 683 megawatt, and they provided about 10% of electricity in the grid in 2020. Now, don't forget that we reached 11% in 2015, but don't forget that the electricity demand is also increasing. So a fleet of power plant that would have met 11% of the electricity demand, today it will be accounting for only about 8% because our base value has gone up. All right. So they're still at 10%, not very fantastic, but it is significant in terms of its achievements. Now, what about the future? What about the future? So, new hydro and hydro biomass and waste to energy projects are in progress, but the development is relatively slow because you could imagine, particularly for mini hydros, most of the good mini hydro sites are already taken up. As we know very well, good projects have been taken up first. That's quite natural when you open a sector to the private sector. They will not look and think exactly the same way as a government. They will go and pick sites which are most profitable to them. So once the most profitable sites are done, the remaining sites which may have a lower energy yield, which may have land-related issues, social issues, and environmental issues, may prevent the remaining mini hydros from going through a faster development process, as we saw in the 1990s and in year 2000 onward. But wind and solar PV have now progressed on competitive bidding. So therefore, what I show is, without the names of power plants, what I show is the price at which electricity is purchased from this taller table is for solar PV. So the early projects, so each line relates to a project. You can go to the web, even the names are apparent because none of these agreements and company names are secret. They are widely open for anybody to see. They fetched a relatively high price, and even up to 23 rupees and 10 cents. Whereas the latter part, particularly the projects that are in the bottom, were on competitive bidding. They were signed up on competitive bidding starting year 2016. And as you will see, when everything else in this country and in the world go up in price, the price at which solar PV is produced in projects, I'm not talking about your rooftops, in projects has come down to 17 rupees 35 from 23.10 that was offered 10 years ago. So projects that were built 10 years ago were offered 23.10, and they are even today getting 23.10. You may be alarmed about it, but the projects that went on competitive bidding have come down to 17.50. But we hear that the competitive bidding rounds that were done in the last 2 years, which have not come into the statistics as yet, were in the range of 12, 13, 14 rupees, that range. Look at the right-hand side diagram, sorry, the table. Once again, I don't show the company names, but each one of these is a project. So you will see that there are projects that are fetching almost 25 rupees, which went on the fixed price, whereas the projects that are not being talked of, the last two here, went on competitive bidding, and they offered 13 rupees for a kilowatt hour. So as you see, almost the wind power prices have halved. The solar park prices have, okay, they've not come as low as half the price, but they have come at least 40%, 35 to 40% lower in current terms. Now, don't forget, between the top project being built and today, there was quite a lot of inflation, exchange rate depreciation, inflation in the country. So if you build all that, this 2310 would possibly today be a lot more expensive than 2310. So competitive bidding has brought in some sense of direction to the renewable energy industry, because finally this electricity has to be sold to customers. It has to be profitable to the developer, and it has to be reasonable to the customer. So now the renewable energy industry is finding its place in which fair play will yield renewable energy projects and profits to developer and benefits to customer as well. Moving on, what happened to solar PV? I'm now gradually coming up to rooftop solar PV. On the left-hand side is a picture of a rural household which had a small solar panel and a DC lighting system supported by a battery. So that was promoted to a large extent until about 2005, at which point the government decided, look, this was fine for the era that we did not have the grid covering the whole country. So these were finally decommissioned when the grid reached the whole country. But what you see on the right-hand side is the next milestone with regard to renewable energy development. In 2008, the government decided that anybody who wants to produce electricity from renewable energy, whatever the source is, solar, wind, mini hydro, and connect it to the grid through his existing electricity connection. Now that's the difference between the projects that I listed earlier, small power producers, and solar rooftops, in which the customer will produce electricity and connect to the grid through his existing electricity connection. So the customer is not a company, customer is himself. Whereas in the projects that I spoke to you earlier, those projects are companies and they enjoy tax-free, duty-free benefits, etc. They produce electricity and sell all the electricity to the grid. Whereas in the solar PV arrangement, there are three options, as you know: a net metering option, net accounting option, net plus option. So 2008 to 2016 was only net metering, that is, you produce and use, and you give the surplus and take the surplus back, net metering. Buyback prices were introduced in 2016. So, which means if you have a surplus, you can sell to the grid at 22 rupees. So right now, we estimate that about 375 megawatt of rooftop capacity is in operation. Now here is the catch. 375 megawatt as of end last year, December last year, was 8% of capacity. A lot of megawatt. But was only 2% of energy. Only small amount of kilowatt hour. So big megawatts, small quantity of kilowatt hours. So that's the limitation of some of the renewable sources. So as long as we fully understand it and work accordingly, then we can go in the right direction without being misled by big megawatt figures. We move on. How the renewable energy development grew. This includes other forms of energy as well. All forms of renewable energy, including rooftops, because earlier I showed you the figure of 10%. Now add 2% of energy from solar rooftops. In 2020, Sri Lanka met 12% of electricity requirements from new renewable sources. Hydro will be extra. So that's the status. Now I gradually move on to the engineering challenges. Engineering challenges. Number one, the hydropower based electricity generation is linked to uses of other resources. That is, the hydropower resource is being used by others. Later on, I will show you some diagrams for irrigation, for drinking water requirements, for water use for day-to-day activities, particularly from smaller streams. So water has other competing and sometimes higher priority uses. As you know very well, drinking water is number one priority. So if the Mahaveli authority says, we have a request from the water board, Kandy water supply is constrained, please open water or please send water downstream from Kotmale. So electricity will be produced, but not exactly at a time that Kotmale chief engineer would like to produce electricity, because the grid is asking electricity at a different time of the day, or maybe storage is asked for. But to support Kandy water supply, Kotmale power plant may be run. I'm just giving you an example. To support Colombo water supply, Lakshapana power plants may be required to run. Drinking water supply, number one. The second priority is irrigation. So water supply for irrigation is the second priority. So therefore, although for power generation, the priority may be to store water, the priority for irrigation will be to release water. Of course, to the power plant producing electricity, but not exactly at the time that it will be optimal for the electricity production. So there is a water management secretariat, because there are a lot of misconceptions that water was released by this engineer, that engineer. You cannot do that, because all the major SOS are instrumented, and there is a standing committee in the water management secretariat reviewing all this information, meeting once a week and agreeing on a water release policy. They get feedback from various water usage areas, from the agrarian officers in those areas. So therefore, there is a widespread misconception that water was released unnecessarily and wasted, etc. I believe it is very difficult for anybody to do something like that. But of course, there are more challenges. Seasonality of renewable resources, interannual variations, then intermittency from solar and wind power. I'll show you some diagrams quickly in a moment. Biomass attracted a lot of enthusiasm, particularly about a decade ago. And people said, look, we have 1 million hectares of marginal land in this country, and 1 million hectares can support 2,500 megawatt of biomass-based power generation. Sri Lanka is still struggling with about 50 megawatt of biomass-based power generation. And the problem is uncertainty in the supply chain. So you might wonder, biomass is very nice, but then it's not picking up. I will summarize the reason in a very simple way. Water is flowing, sun is shining, wind is blowing. So therefore, you build a power plant and produce electricity. But biomass, you have to grow, harvest, and supply. So there is a supply chain uncertainty that is hindering biomass development. Of course, on the technical side, there are difficulties in getting these power plants to contribute to power system stability. Of course, it's a power engineering subject, so I will not go into a lot of details, because stability itself has a very broad meaning, and there are solutions that can be brought into lack of stability. But it will be adequate for me to say that particularly wind and solar are now electronically coupled to the grid. So the turbine, the wind turbine, is not mechanically coupled to the grid. Solar, definitely, as we know, solar power is produced as DC, direct current, and converted to AC. So there is no connection, no mechanical connection between the resource and the grid. So when there is no mechanical connection, it cannot support the stability of a power system in the traditional sense. Of course, there are emerging and proven solutions for that. I said I will show you a diagram. This diagram I picked from a CEB document. It shows how complicated the reservoir network is, and this is only Maha Valley. So if you want to identify things that you know Kotmale, you have heard of it. Upper Kotmale hydropower plant we discussed just now. Upper Kotmale reservoir we just discussed just now. Morogolla is a new power plant under construction now. And those of you who have passed the Polgolla area, you know where Polgolla is, you know where Victoria Reservoir is. And of course, the list goes on. And it shows the integrated manner in which the system operates, because to the right-hand side of this diagram, it's all irrigation tanks. And at the bottom as well in this diagram, as it is laid out, is all irrigation, downstream irrigation requirements. So the system operates under its own constraints and meeting its obligations and producing electricity meanwhile as well. So I said the next one, the first one is linkages with other resource users, and the second one is interannual variations. So see the interannual variations of the energy share from all renewables. So when Sri Lanka had a high renewable share, very high, in certain years 100%. So well before other countries were talking about 100% renewable, Sri Lanka was already 100%. Even in 1990, we were 100%. 1990, we were 100%, but don't forget, only 29% of households had electricity, so the country had to develop. So what we see here is that the impact of interannual variations in terms of the percentage impact onto the grid is smaller, because renewables are now a smaller share, and hydro is also a smaller share of the renewable group increasingly. So your seniors, your parents might say, look, we had blackouts almost every 3 to 4 years, and I marked them with red arrows. And we had 100% renewable energy system, true, but we had to put up with blackouts. So that was the history. And now, of course, we have occasional blackouts for different reasons. The other technical matter that is confronting accelerated solar power development is the intermittency. So this problem has been addressed, and this problem has to be resolved as we go on for larger shares of renewable energy in the form of solar. So this one is actually the solar park in Hambantota. It is managed by Sustainable Energy Authority, the first solar park in the country, which has 740 kilowatt of installed capacity, not too small, not too large either. And these are some rooftop solar. See the rooftop solar on top of your house. If you have a 5 kilowatt, this is probably how it behaves on a particular day. So cloud movements, and it never reached a peak of 5 kilowatt. So here, it's another household in Colombo. It reached its 4 kilowatt. It never reached 4 kilowatt, but it hit about close to 3.2 kilowatt on this day, but very large intermittency. So of course, dispersion of these devices right around the country could allow the intermittency to cancel out, but then it has to be planned for. If it is a fully cloudy day, overcast for 3 days at a stretch, then there has to be additional generating capacity to meet the customer demand. So although a lot of research is going on, still we need to address these problems as we accelerate our renewable energy development targets towards our development targets. So, because sometimes when we keep on developing and talking about the resources, we lose track of the requirements of the grid. So, as you know, electric power system has to produce electricity at the same time the customer wants it. Electricity cannot be stored as electricity. Electricity can be stored in a battery as chemical energy, in a reservoir as water with a potential energy, a potential at a high potential, and electricity can be stored in the form of fuel, in the stockpile, in a coal power plant, in a tank, in an oil power plant. But electricity cannot be stored as electricity. So therefore, it's a unique product, which some people might find it very difficult to understand how it is exactly done. And the challenges that come in when you want to have more and more renewable sources, which have other weaknesses as well, inclusive of not being as robust as the conventional sources of generation. So therefore, attributes of a power system, I will not go into a lot of detail. So the customer demand and electricity production and the little bit of loss in the transmission network should balance out. If the customer is asking too much of electricity, and if the power system cannot produce it, it will lose the equilibrium. So therefore, it has to, most of the time, exactly match. If it approximately matches, then it should be able to correct itself quickly and come back to an exact match. So a power system has to be managed in the form of a dynamically equilibrium at all times. It's dynamic equilibrium. So, of course, Sri Lanka's power system is inherently weak. Therefore, I would not call it a smart grid as yet or anytime soon in the future. We know that even a minor disturbance can cause frequency excursions. The frequency goes up and down and could lead to load shedding as well. So the traditional approach to strengthen the grid is to raise the inertia, larger, faster generators with more spinning reserve. So you engineers know that the rotational kinetic energy is half I omega squared. So an electric power system, if it has a lot of rotational kinetic energy, it is a strong power system. So rotational kinetic energy is there if your speed is high and your inertia is more. Of course, renewable energy in the form of solar PV or wind has no inertia because there is nothing rotating in solar PV and there is no speed as such. So they don't add to the conventional tools that help to stabilize an electric power system. Whereas countries that have a 100 or that had a 100% thermal power system, including nuclear power, they had power systems which are very high in inertia and they were very robust. The frequencies were very stable. So such countries started their race towards renewable energy, starting with a strong power system. Sri Lanka always had a weak power system, and one reason for it to be weak was that we already had a lot of renewable energy in our system. We still have. So in one way, I could say that Sri Lanka missed the bus because Sri Lanka should have first gone to build a robust power system and then ensured reliability and stability, and then go for incremental inputs of renewable energy in increasing quantities. No, Sri Lanka went in a more sustainable and environmental friendly route, in the process compromising the reliability of the power system. So I will move on. This is my last section, financial challenges. What are the challenges with the existing renewable energy power plants? These are the approved costs of the Public Utilities Commission as of year 2019. As you will see here, the cost of electricity production from different sources and the quantities. Of course, the top was the thermal oil-fired generation, Coal came to about 10 rupees. This is 2019 forecast figures. Actuals have been published later in a different format. The pool of renewable energy power plants, look at this number, 1924, 19 rupees and 24. They were not very price competitive. Remember, this was largely dominated by power plants that were commissioned or that were contracted on fixed price, the feed-in tariff. And the rooftop solar came in at 22 rupees. So when you look at these numbers, or when you aggregate these numbers and take the pool average, it was 12 rupees 82 for energy cost only. Don't forget that there are investment costs and there are transmission costs, there are general distribution costs. And here I put everything, and I put everything together: generation, transmission, distribution, and the total is 2184 in 2019. And what was the price of electricity? 1703. So if a businessman was running our electricity industry, he would look at everything that costs more than 1703 and would cut down all of them. But as you see, things that produce electricity below 1703, if you look at the yellow highlight one, all of them were more expensive, including renewable energy. So therefore, a businessman running the electricity industry would cut off renewable energy-based electricity generation, cut off oil-based generation, and manage with large hydro and coal. But the policy is not that. So therefore, Sri Lankans are putting up with this kind of a high price scenario for certain forms of electricity production. But the good news, as I told you earlier, this figure of 1924 is declining. But this figure of 22 is still stuck at 22. Now we are end of year 2021. Still, the rooftop solar PV is purchased at 22 rupees. So moving on, the horizontal line indicates the average price, and the vertical bars indicate the cost of production and delivery of different forms of electricity from different forms of primary sources. So I will skip this slide, and I was talking so much about rooftop solar, and this is how the pricing is arranged for rooftop solar: 22 rupees and 1550 after 8th year. So in my assessment, the profit margin to the investor is an exorbitant 72%, 72% for large rooftop solar PV owners. And I'm sure you agree that this is a mistake that has to be corrected. So when this mistake is corrected, my assessment is that if everybody is getting a return on investment of the order of 11 to 16, then basically the prices have to come down by about 50%, 25% reduction in prices, at least, of rooftop solar is possible. Because I believe that it is not only a technical matter, it is a commercial matter as well. And the commercial angle has to make sure that the investors have a reasonable return on their investment, and we are fair by the electricity customer as well. Because rest of the world, everybody is saying, every journal that you open, every newspaper that you open says renewable energy-based electricity is getting increasingly cheaper by the day for electricity production. But in Sri Lanka, it doesn't happen exactly like that. So therefore, corrections have to be applied so that the industry can continue to grow. Of course, I will not get into the debate about targets, because that's a different study, a different analysis as to what if and can Sri Lanka go for 60%, 70%, 80%, 90%, or even 100% renewable energy-based system. I would say theoretically possible, provided we can meet the engineering challenges and provided Sri Lankans are willing to pay the price of these new sources and the requirements for which investments have to be made to keep the quality of electricity at least at the same level as we have today. Of course, there are some technical challenges in the distribution level. There are more and more fluctuating loads coming into the system. I just had this graph showing how a crane operates in the port. At one moment, it is lifting the container, so it draws power. The next moment, it is lowering the container and it gives power back to the grid. So the fluctuating customer demands, fluctuating electricity production, and the corresponding fluctuation in the voltage. Now, you electrical engineers in my audience will, when you look at this was a measurement done in a household in 2017. The household had a rooftop solar PV system. Look, during the midday, the household voltage, that means not only his voltage, but his neighbor's voltage as well, went way above 250 volt. And the legal limit is 242. The legal limit is 243. Sorry, 243 is the limit. But most of the time, in the middle of the day, the voltage was way above 243. So you might ask, oh, what happened to this household? Maybe it's still like this, but then who cares? Nobody. But we have to care for that because we have to engineer our power system, because someday, sooner or later, this customer's appliances as well as his neighbor's appliances will fail because of this persistently high daytime voltages. So these problems have to be identified and solved, and there are solutions. As I always say, all engineering problems have an engineering solution, provided we are willing to analyze, we are willing to implement, pilot, and then implement, and most importantly, we are willing to pay the price. So there's no point in blaming X, Y, and Z for this problem. This problem has to be resolved. So solutions I've listed here, and a lot of research is going on in universities as well as in CEB, and LECO is supporting research to pilot some of these solutions for this particular problem I brought you in, I explained to you. So I'm coming to the end of the presentation. Solutions to financial constraints also require a lot of political will to overcome commercial and policy lobbies, because as we know, in anything, there are commercial lobbies and policy lobbies in the energy sector and in the renewable energy business as well. But a government has to be able to steer clear of these lobbies, but have a target, and a technically achievable target, and which also has a commercial assessment as well. So correct pricing of rooftop solar PV, competitive bidding for wind and solar investments outside the rooftops are some of the things that we would like to see as we go on into the future, targeting a higher share of renewable energy. Finally, this is my last slide, just to tell you a real world example. An industrial customer, there are many of them who have megawatt scale rooftop solar PV systems. And Sri Lanka offers them perhaps the best investment, which yields a lot more returns than the industry, the manufacturing activity that goes on inside this industry. In my assessment, the fair price that we should pay this solar PV is 11 rupees. But today we are paying him 22. We are paying him 22. What is he doing? He's selling all his electricity at 11 rupees, sorry, at 22 rupees, which is double the price that I consider it to be the fair price. I have a calculation for that. And purchases all his electricity for his industrial operation. And the electricity costs 18 rupees to supply him, but he's given a tariff subsidized, declared to all industries at 11 rupees. So subsidies for sale and subsidies for purchase. So this has to change if we are to accelerate further towards a larger share of renewable energy. So that brings to an end my discussion about historic development and what Sri Lanka has done to answer the question that many people think that Sri Lanka hasn't done anything. Sri Lanka is not doing anything. But now you know that Sri Lanka has actually bent backwards, way ahead of other countries. There are certain countries who still do not have a rooftop solar PV program. I can give you examples. Azerbaijan, Armenia, Uzbekistan, these countries do not have a rooftop solar PV program. Now, in Sri Lanka, from 2008, customers were allowed to connect their solar PV on the rooftops. So it's not that Sri Lanka has not done enough, but we have to do it the correct way, both technically and commercially, if we are to go towards an accelerated pace towards a larger share of renewable energy-based electricity production. Thank you very much.
Right. Thank you very much, sir, for that wonderful presentation and making us aware on present status of electricity generation using renewable energy sources and the challenges where we will be facing in future and the present challenges as well. And thank you very much for explaining all the facts with a lot of interesting examples. So I think right now we can see we have around 146 participants in this webinar. I think you might have a lot of questions to present to the our resource person today. So right now we are getting some questions through the chat box, and you can raise your hand. You can use the raise hand option and request to unmute so that we will be able to provide you an opportunity to ask your questions from the resource person today. So I think we have some interesting questions here right now. Most of the questions are related to solar power field. So let me take some of these questions, sir.
Sure.
Yeah. The first question is, will it, we actually discussed about this. Let me take these questions so that you can give a little awareness on it. Will it be worth to invest in rooftop household solar panel system? I think we discussed about it yet.
Yes, quickly, I'm sure this is a question that many of our engineers have for themselves. And this is a question that their neighbors and friends and colleagues ask them who are non-engineers. So I can say the following: on a commercial and contractual manner, if you sign up with CB or LECO, whoever your supplier is, I can be confident that they will not go back on their agreement, because so far the history of CB and LECO is that whatever they have signed, they have honored. Okay, that's number one. So I only can go by historic performance. So none of the agreements have been renegotiated or forgotten by CB or LECO. So that's one side of it. So I can comfort you on that point. Whether it is worth for you, you will have to do your own calculations, because given the present electricity prices, as you know, electricity, I just showed you in the year 2019, the cost of production and delivery was 21 rupees, but the price of electricity came down to a national average of 17 rupees. So the electricity price you see is a subsidized price. So I don't believe these subsidies will go on forever. There will be corrections all the time. So anyway, I will, it's very difficult for me to tell anybody go ahead with solar or not go ahead with solar. It depends on your perception of your capital cost and your time value of money. What are your alternatives? So do a little bit of a financial analysis that you learned in university or wherever you had your degree. I'm sure your business maths lecturer or the econ lecturer or industrial engineering lecturer would have told you how to set up a small financial model and do your calculation. If you want an answer from me, yes, if you install a good solar PV system, I told you that the customers are being paid a very good price. It's a good business proposition to install solar PV for most of you.
Right. Thank you, sir. And we have one more question related to the efficiency of solar panels. How do we identify efficient solar panel supplier and avoid the use solar panel from other countries supplied in market? Is there any testing method available to differentiate?
Well, I have to admit that I am not an expert on rooftop solar PV. So all what I know is that there are standards. There are standards, but no supplier is legally bound to get SLS for their panels because of the nature in which the international market operates. So I cannot give you a perfect answer as to whether there is a method to measure. What I would generally suggest is to go for a well-established supplier and for a brand of solar panels which are widely in use. So that's the basic advice I can give. But I suggest you can contact the Sustainable Energy Authority. There are a few people who are more knowledgeable than me with regard to the standards and how the compliance is met in Sri Lanka.
Right. And we have one more question related to COVID situation of the country. With the present COVID situation of the country and world, is there any impact in renewable energy generation and investment on renewable energy projects?
I have not observed any COVID-related delays. Of course, the Mana wind power project, the construction happened across several lockdowns. So there were some delays in CEB's own Mana wind power project, but other activities are going on. I have not observed any significant delays because most of the things that are coming up are solar parks and the private sector wind parks. So there may be some delays, obviously, owing to multiple reasons, but there is no major delays as such. There are delays, but I don't think they are related to COVID. They are related to approval process, environmental approval, and there is a bundle of projects that are awaiting the ministry approval for the last so many months. And there is conflict within the government as to which way should go for renewables. So because of those, perhaps certain projects may get delayed, but not necessarily due to COVID.
All right. There's one more question related to present economical situation. As the current energy scenario, 41% covered by the oil, but the energy security of the Sri Lanka is in question due to the USD problem facing in the country. So what's your view on this, and what are the future plans to overcome and to ensure the energy security of the country?
Fine. Let me give you some numbers first. We expect this year, or rather, let's say 22, Norachole power plant, which runs on imported coal, to meet about 32% of electricity requirement. And as you know, Norachole, even with increased coal prices went up from about $70 to $140, depending on where you purchase, the bidding, etc. But basically, coal prices doubled when compared with the price 1 year ago. Let's put it that way. So therefore, but still, even with the double the prices, that is the cheapest power plant to operate. It's cheaper than renewables as well. But then we have only one Norachole, so probably 32% of energy will come from that power plant next year. And even with renewable energy development that is going on, if next year is an average hydrological year, most likely we will still have to get another 27% of energy from oil. Now that is the dangerous part, because as you know, electricity from oil is about 3 times the price of electricity from coal, right? It's definitely more expensive than renewables. So therefore, it's not 41%. If you want to look at a percentage, it's 32 plus 27. which is much larger than 41%. 32 plus 27 is about 60 percent to come on imported fuels. That's the issue. So again, if you want some numbers, Norwich requires about 2 million tons of coal. So you can multiply 2 million by $140 a ton, and you have a figure of about $280 million to import coal for Norwich, and probably even more than that to import oil for the 27% energy requirement, because oil is a lot more expensive. So therefore, probably we are looking at something like $500 million or more for oil, thermal fuel requirements, coal and oil for power sector. So like anything else, the impact of the dollar crisis will be similar to the power sector. So it depends on how the government will prioritize in providing fuels. Whether they will give priority to the power sector or to the transport sector, I do not know. So the problem will have to be confronted as we go into the future. So I can't say how it will be handled, but I can only give you the magnitude of the problem. But on the other hand, if we had the gas terminal done by 2017, as it was originally planned, then the amount of money that we spend on oil would have been less, and in some situations, even less than coal-fired generation. If we had the gas terminal, so we don't have the gas terminal, we are still debating about it. So even for the next 2-3 years, we will not have a gas terminal. So in fact, we missed out on getting the benefit of gas, and the low gas price era actually probably is over. So we may still have this terminal after this debate is over. As you know very well, there's a huge debate going on. After this debate is over, probably we'll have a gas terminal, but we may not have the advantage that we plan to have from gas when we ultimately build it in 2025 or 10 years later. Thank you.
As I said, you will be able to use the, you can raise your hand and present your questions as well, so that we can unmute you and give the opportunity to present your question. So we have some more questions coming in the chat box. I think we are getting a lot of questions in solar power as well. One interesting question: how do we manage waste from the renewable energy sources and green technologies, such as wind turbine blades, solar panels, and batteries? Is there any recycling process available?
In Sri Lanka, no. Sri Lanka has not even thought of it, right? So in fact, our first wind power plant, first commercial wind power plant was commissioned in 2010. So that hopefully will come to end of contract by 2030. It's not too far from now. So come 2030, there will be a set of 3 blades into 8. So 24 long blades, each of about 30 meters fiber, and then steel towers and various equipment which have to be decommissioned, because I doubt whether the private sector will run 20-year-old wind turbines come 2030. They will build wind turbines which are 3 times larger. So therefore, there will be a lot of waste created. We still have not even thought of it. And similarly, solar panels and batteries as well. But for batteries, certainly internationally, there are recycling methods available. But I doubt whether for solar, it has been resolved as yet as to what to do with solar PV, except short of crushing and disposing of it. Whether there is anything else, I really do not know.
And we have a question on offshore wind. Is there any development towards offshore wind power in Sri Lanka, I think? Yeah.
There is an ongoing study supported by the World Bank. I'm not fully aware of the outcomes of the study, but there is an ongoing study to assess the offshore wind potential. So once again, the focus will be onto the offshore areas of MENA, but because as you know, MENA is a good windy zone out of even among the sites in the north. MENA up to Punarin is the best wind zone, and we are at an advantage really, because the seas of MENA and even the seas of Punarin are relatively shallow. And as you observe, there are no shipping routes passing MENA. Why aren't there any shipping routes? Because the ocean is not deep enough. Because as you know, for a ship, for a big commercial ship to move, the depth of water should be as much as 20 meters if you want a huge ship to move. So, but the area offshore MENA, particularly between MENA and Punarin, is probably at most 8 meters, 6 meters, etc. So, which is in terms of foundations, it would be cheaper. But there are other constraints, there are other countries such as the Setu Samudra. Will the Indians want to again implement the Setu Samudra concept, etc. Indians wanted a sea channel across the Pork Strait. Will it come in? So will it have any impact, etc.? So there are other constraints. There are studies going on, but I've not seen any outputs yet. But it will be very expensive, as you can imagine. Offshore wind is very expensive. So my suggestion is to go for onshore to the best possible extent and then go offshore.
Thank you, sir. And we have one more interesting question. How fair is to exempt biomass power plants from competitive basis? Most developers complain that competitive basis is very unfavorable for them.
Yes. Okay. Of course, in real life, if competition is not fair, don't participate in competition, because nobody is compelling anybody to build any power plants. So therefore, if a bidder says competitive basis is not good for me, then he is not a sharp businessman. That's my view, because he has to look at his costs, do proper financial modeling, and do his engineering properly, and do the costing and send the bid. So I fail to understand why developers complain competitive basis is unfavorable. Because on the other hand, a fixed price is also not favorable, because we have to be fair by the society. Now you tell me whether there is any business in this world where somebody says, I will purchase all your production for the next 20 years without saying no at all, and at the following price. Is there any other business in this world? That includes your rooftop as well. Somebody says, I will purchase all your output, even when I don't want it. Now, in November, as you know, there was reservoir spilling. So reservoirs are spilling because the rainfall is so good. And CEB is purchasing renewable energy from your rooftop at 22 rupees. Because energy economists will tell you, if a reservoir is spilling, the value of energy is zero. The value of the incremental value of energy is zero. So therefore, it should not be purchasing anything. So if Sri Lanka had a free market, CB would have said no purchase from solar PV until reservoir spilling is closed. So no, the best possible contract is given to rooftop solar PV and others as well. But finally, we have to be fair by the society, that we get renewable energy developed at a fair price, because the contracts are so attractive. So I fail to understand why developers don't like competitive bidding, because competitive bidding does the price discovery. So if it is not competitive, you saw the numbers. I showed you the numbers. The fixed price, although I was also party to establish the fixed price mechanism to get the system accelerated, because to get the investors used to this, to get the bankers used to this, we had to offer the fixed price or feed-in tariff. So that I was one of the strongest supporters, in spite of many protests from some others, to offer the fixed price, to get the industry going. But when the industry is large, 250 projects in operation, so much of experience among our local investors, engineers, bankers, etc., then we must now move on from a fixed price mechanism to a competitive mechanism in which we be more fairer to the society at large who will actually use this electricity. Finally, quickly, biomass power plants. I'm actually not exactly sure what the legal position is. If you take a biomass power plant, whether CB will sign up with you. So, but what I understand is that the non-competitive price for biomass is still open because still it is a picking up form of renewable energy-based electricity generation. So, because as I said, we have less than 50 megawatt of biomass-based power generation, whereas in everything else, mini hydro 350 megawatt, wind, I think almost 300 megawatt, etc. So, it's large quantities are available and a lot of experience.
And I can see Devin is raising his hand. So let me unmute him. Yeah,
Hello,
Devin,
can you hear me?
Yeah. Yes, we can hear you. Please go ahead with your question.
Good evening, sir. Just a small question. Now, as we know that rooftop solar power generations are working in unity power factor, right? And can't we adjust it for a power factor other than unity power factor? And obviously we can, but have anybody conducted any cost analysis on how to pay the rooftop solar personals if we go for another power factor rather than unity power factor? Because because the voltage rising in the daytime, and that can be reduced if we can use solar PVs as STATCOMs or power compensators.
Yes. There have been studies both at Peradeniya University and Moratuwa and by CEB as well. But I don't think the studies have gone as far as offering an additional incentive for people to go in for smarter inverters, which can operate at different required power factor and thereby supporting the network to manage the voltages. So the studies have not gone so far. In fact, I look forward to being in a team that will actually practically implement a smart inverter program in one or two of the networks, provided the funding comes our way. We hope to implement it on a pilot scale and see the results. But having said that, we also need to realize that the distribution lines have a lower X to R ratio. So therefore, the amount of voltage regulation that you can do by absorbing or injective reactive power is not as great in percentage terms as much as you have in transmission lines. So that having that constraint in mind also, but the calculations I have seen is that yes, it is possible. There are benefits of doing it, but how exactly it will be done has to be, the calculations are not that complicated, but then they have to be practically implemented in one or two pilots in the country. And then with that experience, it is possible to go in for a regulation or a guideline to do that. So I wish that the electricity suppliers take additional interest on this, and Sustainable Energy Authority and the universities get together and do this, or one entity to do it and publish the results and get it regularized through a proper mechanism. So we are getting there, but not as fast as I would like it to be.
So now it's 7:23. I think let's address two more questions and let's conclude the session for today. And I'll couple two questions. Right. So we have one question about the controlling. Any plan to introduce inbuilt generation control mechanism to large-scale solar, wind, and mini hydro to reduce the intermittence in future operations by CEB? And I'm going to couple it with another question. When it comes to renewable energy generation, the main issue is storing technology. What are the initiatives taken so far from the relevant authorities?
Right, I'll take the second question first. Storage. Storage, as I see from a CEB point of view, CEB is going ahead with the recommendation to build a pumped storage power plant. Pumped storage power plant, as you know, is a two reservoir system in which water is recycled in a way, so that electricity is stored in the form of water at a high elevation when you have surplus. And it acts as a load as well as a generator, depending on whether you are surplus with energy in the system or deficit. So that project, I believe, is proceeding. It has not entered construction or anywhere near at the moment. Then I've also seen recommendations to bring in battery storage for at a system level. Now, battery storage can have different purposes at different levels. So if you are to resolve the voltage rise problem in a distribution network, then it has to be a localized battery to resolve that problem. But if you are looking for a battery to resolve the intermittency of a solar park, then it has to be implemented at the park level or at the substation level. If you are looking for a battery to stabilize the grid in the face of a large quantity of renewables being on the system, whereas our system is inherently a weak power system, then you need to look at large centralized battery banks to support the system stability against transients. So to my knowledge, CEB is planning for centralized batteries for management of intermittency and transients. And there are studies going on at the moment by, once again, universities and by my team as well. It's good for many people to do studies and research and try to go into a pilot in which we try to resolve the distribution lines that are showing over voltages. It is not only that it's a customer solar PV. There are other CEB control systems also that can be fine-tuned to manage this voltage issue. So in the ultimate analysis, it could be the low voltage problems when a lot of solar PV is integrated at the distribution level. There are multiple solutions. So it may be a combination of solutions of localized battery storage, smarter inverters, as there was a question on how the inverter could pump in reactive power or absorb reactive power depending on the requirement, and also in certain situations have another distribution line supporting the solar PV, particularly in areas where the lines are overhead. So it's a combination of solutions that will take us there. And in my view, we need to quickly get these things piloted and implemented and brought into the regulations. Because I will be unhappy. Of course, I have issues about pricing, but I will be unhappy if a customer is turned back when he goes with an application to say that, you know, your line is full, we cannot accommodate your rooftop solar PV. That is not engineering. Engineering will be to find a solution for that. True, there is a financial matter. Let us solve the financial matter. But from an engineering point of view, we have to solve this problem.
Right. So let me take the final question to you. What are your thoughts on floating solar power plants? Yeah.
I'm not an expert on floating solar. In fact, I'm not an expert on solar either. But I can only make some comments. Floating solar, it helps us to optimize the land use because remember, Sri Lanka is a high population density country, almost 350 people per square meter. From a world scale, we are a country of high population density. So it always occurs to me as to whether we should dedicate land for solar PV, because our land will be required for agriculture and forestry and other productive uses rather than dedicating this land for solar PV. So therefore, my first preference is to cover the rooftops. Cover the rooftops which are idling there, solve the problems, both technical and financial, and cover the rooftops. And then go for land. And when you go for land, look at floating solar as well. Floating solar is more expensive because it has various other design requirements and design standards that are required because you are in a moist environment. But floating solar definitely is a very good option that we should at least pilot. Of course, I know there's a floating solar piloted at Jaffna University Engineering Faculty in Kilinochchi. I have seen it. Okay, that's a university pilot. Then we need to get a commercial level pilot and understand it. And that's how mini hydro was done. That's how wind was done. Nothing was done at a huge scale on day one. So that's how mini hydro was done. That's how biomass power plants were done. In fact, the first pilot biomass power plant is not even in existence today. It had to be shut down. All right. So, but through that, people learned quite a lot. So there is a learning exercise which has a cost, and we should implement and make it a learning exercise. Our problem here is that with the first floating solar, there'll be a lot of publicity that, everything hereafter will be floating solar, upsetting the whole process that is ongoing at the moment. So, but then we'll have to go into all these things as well. We recently did a feasibility study for a floating solar system in Maldives. Maldives, as you know, it has a lot of sea space, but hardly any land space. So therefore, there are economic constraints when you do that. And unlike for us, it's open sea for them. So it'll be a lot more expensive than having a floating solar in one of our irrigation reservoirs.
So thank you very much, sir, for addressing all the questions. And I think we can see a lot of engagement in the chat box. We are getting a lot of questions, yet we have very limited time. So sorry for not being able to address all the questions, yet hopefully in future, let's organize another webinar, maybe an extension of this webinar in future to address all those questions. So thank you very much, sir, for your great presentation and addressing all the questions raised by the audience, and coming up with a lot of insights in the present status of renewable energy usage in the field of power generation. And as engineers, we tend to forget mostly about the financial viability. Thank you very much, sir, for addressing that as well. So with that, let me conclude this session, and let me hand over the control to the chairman of IESL Puttalam District Center to present the vote of thanks. Over to you, chairman.
Thank you, Shabri. I'm sure we had a fruitful webinar on renewable energy for electricity generation, achievement and challenges. It is pleasure to appreciate our resource person today, Dr. Tilak Siyambalapitiya. Thank you very much, sir, sharing your knowledge and experience with us. Our gratitude goes to IESL Head Office official for all cooperation and facilitation given us. And I have to appreciate all IESL Puttalam District Center committee members. Your courage and support end up with successful webinar. Finally, I must thank all of you who participate for the event. Thank you very much.
Thank you, Chairman of IESL Puttalam District Center, Sanjeev Priyadarshana, for presenting the vote of thanks. And I hope you all had a fruitful day. We discussed a lot of topics with a lot of insights in the field of renewable energy. So with that, let me conclude the session for today. We'll be coming up with more webinars in future in these timely topics in future. So with that, let me conclude the session, and goodbye to everyone. Have a great day.
Good night. Thank you.